Hi everyone, my name is William Kohler, and today I'm going to be telling you about one of the possible great potentials that hydrothermal vents present, their ability to use hydrogen fuel cells to generate electricity and light. Now, unlike most other presentations thus far, I will be focusing on the geological abilities of vents. I'll admit, coming to a solid conclusion when it comes to finding a present-day applicable use for harnessing energy through vents requires a bit of imagination. But all this aside, I will be focusing on their potential, and I hope to leave you all coming away from this feeling optimistic. An overview of what we're going to try to pick up on today is I'm going to try to tell you what makes hydrothermal vents a potential source to harness energy from. I will be covering the importance of green energy, what hydrothermal energy is and how it differs from other renewables, what a fuel cell is and how it works, weaknesses in the technology, and what the technology can be used for. So let's get into it. Now, for those of you that need a refresher, hydrothermal vents are environments that disperse hot mineral-rich fluids from oceanic crust through a process which is geologically driven by magmatism. They form when cold seawater percolates down through crevices in oceanic crust, also known as spreading centers or subduction zones, which are places on Earth where tectonic plates separate, shift, or collide with one another. The cold seawater is then heated by magma, where it is enriched with minerals in the crust, where the fluid then diffuses, mixing with the seawater to form hydrothermal vents. The part of the reaction that is important in my findings is the chemical gradient between the hydrothermal fluids and ambient seawater, and it's the difference between the two which has the potential to generate electricity. As is known, climate change is one of, if not the largest threat to our Earth. Climate change is defined as the long-term shifts in temperatures and weather patterns, mainly caused by human activities, especially through the burning of fossil fuels. Now, I'm not trying to make an argument where I concede to our looming fate. I myself have a cautious amount of optimism, for I never want to rule out the ingenuity of humanity. As you see on this graph, this is what our current course of temperature increase looks like if we were to continue to live as wastefully and unregulated as we do now, with the bottom showing the outcome if we were to take drastic preventative actions, and the middle area being a region of uncertainty. Now, there are several ways right now which we can cut down on our greenhouse gas emissions, those being mostly in the realm of consuming fewer resources, whether it be having a more robust public transport system, consuming fewer animal products, or having our buildings be designed more efficiently, among other things. These are all things which on their own would be a massive step in the right direction. However, they can't be done without concurrence from the largest culprit of emissions according to the EPA, that being electricity and heat production. Electricity is something that we cannot live without at this point. It is considered to be a basic human right. And for us, the best way we can tackle this problem is through the use of green energy sources, harnessing the geological processes of Earth so that we can use them on a renewable basis. One of those potential sources being the aforementioned hydrothermal vents. For an intro to renewable energy, having already factored in the issue of climate change, the other pressing question regarding energy is how we're going to have the ability to produce enough of it to support our population in the future. The solution to that is renewable energy. Renewable energy is defined as energy that is collected from renewable resources that are naturally replenished on a human timescale. Collectively, we need to be able to set up enough sources of renewable energy before we deplete our non-renewables, lest we suffer from an impending energy crisis. Even now, with the war in Ukraine, we are seeing how fragile society can become when we are so heavily reliant on coal and natural gas. Potentially new sources of renewables intrigue so many because finding an untapped source of energy is something that has the possibility of being a key part in building the foundation to structure society entirely from renewables. Some of our most established forms of renewables are solar, wind, geothermal, and while not renewable, a greener form of energy, that being nuclear. Now, you may be wondering, what is the difference between hydrothermal fuel cells and other renewable energies? Well, in the ongoing search for new sources of renewable energy, one of the greatest issues that interferes with practicality of reliability. Most are aware of the presence of renewables such as wind turbines and solar The biggest problem with those is that it is not always windy and it is not always clear and sunny. In addition, the fear factor of meltdowns is enough to deter large swaths of the public from being in favor of consistent nuclear energy. These shortcomings are what the non-renewable energy sector grasps onto with an iron fist. This makes it so that the crowning achievement of renewable energy is a consistent, cost-effective, and high-power source of energy. While it is worth investigating, hydrothermal vent energy will likely not be used on a commercial scale within our lifetime. However, I just said commercially. The research potential for this energy could be valuable. One of the questions going into this was understanding how hydrothermal energy is any different than geothermal energy. Out of all the renewables available to us, it appeared that geothermal would have the highest amount of similarities to hydrothermal in terms of how they produce energy, in contrast to other resources. This theory was quickly debunked, however, as I soon learned that while both follow similar geological processes, the way that energy is harnessed at hydrothermal vents is through fuel cells, rather than the traditional turbine and generator method that geothermal power plants use. Now, you may be wondering, what are fuel cells, and how are we going to harness energy from these vents? I'm not going to go into major depth on how fuel cells work, but I'm going to try to convey them to a point where you can understand about why they matter. To know why fuel cells were the method that was landed upon, you need a bit of background to the technology. Now, the real-world testing of electricity generation at hydrothermal vents is something that only came to existence in October of 2012. So with less than 10 years of data, researching this technology has been rather difficult, compared to something like solar energy, which was conceived nearly 70 years ago. The fact is, it is relatively new, gives it the possibility of changing in the future, as methods are still being improved upon. With that out of the way electricity is traditionally generated is through a process where a blade is forced to spin via heat or wind, where the blade then causes a copper wire to rotate around a magnet, stripping it of its electrons, and then those electrons are sent through a wire, therefore creating an electrical current. Unlike this, however, if you recall what I said, it is the chemical gradient between the hydrothermal fluids and ambient seawater which gives us the potential to generate electricity. But what does this mean, and how is this energy captured? Well, the method of extracting energy is done by a fuel cell. The reason that we opt to use a fuel cell over standard batteries is that batteries have the problem of being a closed cell, which stores all their energy in the chemicals they contain. While some can be recharged, they rely on chemicals which have the issue where they degrade after each recharge. A fuel cell is in essence a battery, but with the key difference that when they are maintained with a constant stream of fuel, in this case, hydrothermal fluids, they don't need to be recharged. The compound which fuel cells catalyze is typically a form of H2, and in the case of hydrothermal vents, they emit hydrogen and hydrogen sulfide, both being consistent of H2. With a constant input of hydrogen from hydrothermal vents and oxygen from ambient seawater, we have the two components that are required for energy output from a fuel cell. The point of a fuel cell is to separate the process of mixing of two different fluids in order to capture energy. Otherwise, they would react in a way where the energy couldn't be harnessed. The way they are kept separate is through an NaCl-based polymer membrane called an electrolyte, which is the part in the middle of the fuel cell. The electrolyte prevents the hydrogen and oxygen molecules from passing through it. However, it does allow for the positively charged hydrogen ions known as protons to pass through. When the hydrogen molecules are passed over a catalyst made of platinum or iridium, known as the anode, half of the electrode, they are split into their respective protons and electrons. The splitting process is known as oxidation. The part of the equation that is valuable to us are the hydrogen's electrons that are produced as a result. When we take them and we put them into an electrical circuit, this results in electricity. The reason why seawater is another important part of this equation is because it is needed on the other side of the electrolyte membrane for the oxygen that it contains. Now, we've already split the hydrogen into its protons and electrons, and since the electrons are being manifested into electricity, where do the leftover protons go? Well, it is the work of the cathode on the other side of the fuel cell, which allows those leftover protons to catalyze with the incoming stream of oxygen, forming water, and integrating them into the surrounding seawater. With this whole process over, the only byproducts are the sulfur that was left over From the anodes, catalyzation of hydrogen sulfide from the vents, water. From the cathode, catalyzation of oxygen and the hydrogen proton. And lastly, the electrons, which are used for electricity. Now what this looks like is the fuel cells place anode electrodes in the hydrothermal fluid, while the cathode is placed in nearby seawater in order to create a chemical gradient, which produces an electrical current. The reason why part of the input says half O2 is because it is to balance out the chemical equation for water, which is 2H2O2. Another possible type of energy production would be through thermoelectric generators. Rather than hydrogen fuel cells, this type of energy focuses on exploiting the heat potential of hydrothermal vents rather than the chemical gradient. The reason why researchers have opted for fuel cells until now was because they were able to generate a higher output of electricity this way, since they used a corrosive resistant electrode, which made it so the energy output was greater than it would have been if they were to use a gradient based on temperature difference between the hydrothermal fluid and seawater to generate electricity. This method is called thermoelectric conversion. How are they installed? Rather than you might be led to believe, the fuel cells are not directly placed over pre-existing vents, and instead installed over holes drilled for the purpose of being wells near hydrothermal zones. These man-made holes are widely referred to as artificial vents. The discharge fluxes of the hydrothermal fluids and the patterns of the artificial vents can be mechanically controlled, meaning that the reason why artificial vents are preferable is that if the fuel cells were put over pre-existing vents, they would have less control in reaching a desired output of hydrothermal fluids. Also to note, there are no significant differences in the temperature and chemical compounds of the hydrothermal fluids when observed between natural and artificial vents. Now, to my knowledge, this is the only known video of a fuel cell working at a hydrothermal vent. This video is from one of the case studies which we have access to that took place off the coast of Japan in Okinawa in October of 2010. These tests took place during the Integrated Ocean Drilling Program, which is a program that uses drilling in order to monitor and sample sub-seafloor environments. During one of their outings, they created several artificial vents by drilling wells in the Heha North Hydrothermal Field off the Okinawa Trough in Japan. Of the artificial vents they created, one was capable of discharging fluids at a high of 309 degrees Celsius. Now this was at a water depth of only around 1,000 meters, which is notable since most vents occurred at an average depth of 2,100 meters, making this area a lower pressure to subject a fuel cell to. And this is where it took place. At risk of making fuel cells at hydrothermal vents sound like the perfect form of energy, I want to bring up some caveats. For starters, hydrothermal vents produce an extremely low amount of energy. The hydrothermal fuel cells at the Okinawa Trough in Japan were producing 21 milliwatts, which is capable of only powering 3 LED lights. This productivity is peanuts compared to an average offshore wind turbine, which has a capacity of 2.5 to 3 megawatts. This disparity is crazier than you might think. This gives offshore wind turbines a 2.5 to 3 billion time output as hydrothermal fuel cells at hydrothermal vents. Now, in all fairness, this technology is quite new. Imagine if we had been expecting full productivity from solar panels immediately upon their inception. Another issue is vents only remain active for 1 to 2 years on average. This limited time span makes it so every few years the devices used for energy extraction would have to be picked up and relocated. While this is an inconvenience, it is one of the drawbacks that needs to be dealt with for this specific renewable. Also, active vent zones only make up around 50 square kilometers in total, meaning that they are roughly active vent zones, that is, meaning that they are only half the size of Disney World. This factor alone means that there is a hard limit to the amount of energy that can ever be harnessed. Concerns about installation of fuel cells also involve local fauna. One of the larger concerns about having an abundant system of fuel cells blanketing the seafloor is that they would redirect resources from local ecology. Even though these fuel cells would not directly disturb established vents, their presence alone could weaken their ecosystems if done on a large enough scale. Now, what previous problems does this energy solve? And where would this be appreciated? Now, after I've spent some time slandering the output of electricity of hydrothermal fuel cells, you may be wondering, why should we even be investing time and resources into researching a technology which grants nothing but a way of generating meager amounts of electricity? Well, that's a fair question, especially when we have other forms of renewables. My best answer for that is that it is important where it is needed. Out in the ocean or in the deep sea, you are hard pressed to find a source of renewable energy to work off of. Deep sea technologies have long been limited by the requirement of batteries or power cables in order to function. In submarines, for instance, replacing batteries has a high cost. For seafloor technologies, the distribution and rollout of power cables isn't practical. These issues are necessary to solve if we ever hope to do long-term sea ocean exploration, and they can be done so through the machinery of hydrogen fuel cells and thermoelectric converters. There are also some incentives to investing in this energy, but what are they? As human expansion continues, the need for minerals follows suit. Hydrothermal vents and their surrounding areas are rich in valuable minerals, which are still untapped. The reason why they are yet to be mined is because of the cost of extraction, which does not yet outweigh the profit, in part due to the amount of energy required to reach the seafloor and harvest these minerals. An answer to this hindrance could feasibly be solved by a mine which doesn't require input from the surface to function, where its electricity needs would be supplied by energy available at the vents. While this sounds like a remarkable way to supply humanity with minerals through green energy, there are some costs that need to be factored in. The main factor being vent species. Vent species are known to be ecologically resistant, being able to rebound from mass deaths with quick primary succession. However, the effects caused by mining could leave long-term harm to these communities. We've seen experimental drilling have minor but noticeable effects on the health of vent communities. For instance, the drilling which took place off the previously mentioned Okinawa Trough was enough to hasten the hydrothermal fluid output, changing the expected diversity of species to be present. If this one small drilling impact had a noticeable change, there was a fair concern that a large-scale operational mine could irreparably damage a vent ecosystem. Another potential is more of a hypothetical, and more important when considering the future. Humanity could possibly reach a point where we have tapped into all of our renewable energy sources from a plethora of different locations. We may get to a point where even sources that produce relatively small amounts of electricity are useful in the far future when other renewables are saturated. The question that lies upon us is how much we are willing to pay to extract said energy. Even though this is all speculation, it is another reason to develop this technology. Well, the clearest way to improve the fuel cell rig would be to improve upon the materials and structures of the electrodes. Currently, they are made to be resilient to pressure, but this has come at optimizing power production. Even with that considered, the pressure being administered onto fuel cells is nothing to brush aside. Another possibility to look at fuel cells would be thermoelectric converters and other methods of energy capture. Thermoelectric converters use a heat gradient of vents and are a newer technology, which is experimentally capable of extracting 2.6 to 3.9 watts of electricity, which is an almost 200-fold increase to fuel cells. Similar to how fuel cells exploit the gradient between hydrogen and oxygen, thermoelectric converters exploit the gradient between hot and cold regions through a process called the thermoelectric effect. Through this effect, heat can be concentrated from vents and put into a thermoelectric generator, where over a metallic medium, the hot side, being supplied by active vent flow, moves towards the colder side met by seawater. This heat exchange switches the change in the metallic medium, and as a result produces a stream of electrons. Some closing thoughts. Hydrothermal vents are sites which offer great potentials of energy. Their energy comes from the hydrogen-abundant hydrothermal fluids that are enriched with electrons, that which when they come into contact with cold seawater that contains cations or electron-depleted ions, there is potential to generate electricity. I don't believe that as far as renewable energy goes, there is one best method. Based on local climate and environmental characteristics, there are different ways to source energy. You can look at a country such as Iceland, which has previously had issues when it's come to keeping electricity cheap and accessible. So they took what natural processes they had available to them, in this case their positioning over tectonic plates, and started investing in expensive geothermal energy. But eventually it became worth it to them, and now as much as 85% of the houses across the country are powered by geothermal energy. As much as I wish they were right now, the application of fuel cells is not currently a key to solving the world's need for energy, and that's okay. Similar to the problem-solving approach of Iceland using its environment to create electricity, tapping into the potential events, whether it be through fuel cells, hydroelectric converters, or a combination of the two, their existence offers us more free rein to conduct research out of the sea with fewer constraints on the time span for consistent supply of energy, which is needed for a resupply of batteries or petrol. Thank you everyone for watching, and I hope you learned something.